Okay, we're going to continue on with part 2 of chapter 7 of conceptual physics. We're going to discuss mechanical energy in particular, potential and kinetic energy. So mechanical energy is, let me dismiss this, mechanical energy is due to position or to motion or both. As a matter of fact, we'll see if you throw a ball up in the air, as it rises, it transfers from kinetic energy to potential energy, becomes all potential energy at the apex of its travel, and then begins a conversion of potential energy to kinetic energy. And there's a constant transfer of potential and kinetic energy. And we'll see that with either a spring pendulum or a regular swinging pendulum. So there are two forms of mechanical energy: potential energy and kinetic energy. And potential energy is the energy of position. Whether it's you hold a mass 1 meter off the ground, or you compress a spring so many centimeters, it has the potential to release the spring, and let's say throw out a ball bearing or something like that. So potential energy is the energy of position. Kinetic energy is the energy of motion. If you have velocity, you have kinetic energies. If there's no motion, then you have no kinetic energy. Okay, potential energy is stored energy held in readiness with a potential for doing work. Example, a stretched bow has stored energy that can do work on an arrow. The stretched rubber band of a slingshot has stored energy and is capable of doing work. If you compress a spring in a little toy gun, it has the potential to fire a little dart. If you hold a pile driver so many meters above a stake, when you drop it, it will drive in the stake. So in the up position, it has potential energy to do work. So its potential energy is due to an elevated position. Now that has to do with gravitational potential energy. In the case of the bowstring and the compressed spring in a toy gun, let's say, that's not necessarily, it's not necessarily from elevated position, but gravitational potential energy is related to elevated position. So water in an elevated reservoir, the raised arm of a pile driver, these are examples of gravitational potential energy. Okay, this is equal to work required to lift an object. This is the force required to counteract the object's weight times the vertical distance of the lift. So if you lift something up, you are given it gravitational potential energy. In equation form, the potential energy equals the weight times the height. Well, what is weight? Weight is mass times the gravitational acceleration, g. So the weight times the height is mgh. Mass times the gravitational acceleration times the height, mgh. That is potential energy. That is gravitational potential energy. Okay, there's a crate lifted by a pulley have increased potential energy relative to the floor. Does a crate lifted by a pulley have increased potential energy relative to the floor? Well, if you raise it up, if you were to release that crate, it has energy enough to do some damage. It could crush your toe or something like that. So the answer is yes, it does have, but it does, when you lift a crate above the floor, it does have potential energy. If the crate were twice as heavy, its increase in potential energy would be twice as great. So the mass is double, then mg is double, and so the mgh is double if you keep the height the same. Okay, potential energy. Potential energy of a 10 Newton ball is the same in all three cases because the work done in elevating it is the same. So in other words, it doesn't matter the path you take to raise it 3 meters. The here lifting it straight up, or here, this, you can recognize this as a 3, 4, 5 triangle. You go 5 meters this way, well, you've gone 3 meters up. Or if you go in this step mode, all of them, the mgh is the mass times gravitational acceleration times 3 meters, irrespective of how you got there. Okay. Now, kinetic energy, so potential energy is the energy of position. Kinetic energy is the energy of motion of an object. It's given by 1/2 the mass of the object times the square of its speed. Momentum, we learned, was mv, mass times velocity, whereas kinetic energy is 1/2 times the mass times velocity squared. So if the speed is doubled, the kinetic energy quadruples. If you double the speed, momentum is only doubled, but the kinetic energy is increases by 4, by a factor of 4. Okay. Does a car with momentum have kinetic energy? Yes, because the car is in motion. Only if the car is accelerating, only if the car is not accelerating, or no. Well, if there's motion, then there is kinetic energy. So if a car has momentum, it is necessarily in motion. Remember, it's mv. Momentum is mv. Anything in motion necessarily has kinetic energy, regardless of whether it's accelerating or not. Okay. Kinetic energy of a moving object equals to the work required to bring it from rest to its speed, equivalent to the work the object can do while being brought to rest. If the object is accelerated from rest with force F through a distance d, then its speed v can be determined using the final kinetic energy equals the work done. So 1/2 mv squared equals force times distance. So we can use this little formula, 1/2 mv squared equals fd. We can use that to solve problems. Okay, and that's the end of the potential and kinetic energy, part 2 of chapter 7. We'll continue on with part 3 in the next video.